Good morning, everyone. I am Usman K, Assistant Professor, BITM Ballari. First, I welcome you all to my seventh video lecture on Model 4. So, in the previous video lecture, we discussed about perspective projection coordinates, and also we discussed what are the various OpenGL functions we are using to use various types of projections. Like we are using GL ortho function, we are using GL frustum function, next we are using GLU perspective function, next we are using GL lookup functions. These are the various types of functions we are using in our OpenGL program to project three-dimensional object on the two-dimensional screen of the monitor. Next, we also discussed perspective projection transformation coordinates. Now, I also explained whenever we want to determine what are the perspective projection transformation coordinates, we supposed to determine projection of the line segment or projection of the given object on the view plane, and we also determine what is the position of the projection plane. So as we discussed in the previous video lecture, you can place the projection plane in three different places, and we also discussed what is the position of the projection reference point when we are using synthetic camera. So these 3 points clearly specifies how we can implement synthetic camera model in OpenGL program to create synthetic object and also to display synthetic object on the screen of the monitor. So what I am telling is here, we are creating synthetic object. After creating synthetic object, we are displaying synthetic object on the screen of the monitor using synthetic camera model. So when we are using perspective projections in our synthetic camera model, we need to determine all these three concepts. So as we discussed already, how to determine projection of the line segment on the view plane. But as I said in the previous slide, we need to derive one equation here to determine what is the projection of this point P on the projection plane, that is called P dash. So this derivation I did not explain in the previous video lecture. So today I would like to determine what is the projection point of this point P on the view plane. So determining the coordinate of the projection point on the view plane is nothing but xp, yp and zp. So as I discussed in the previous class, uh, whenever we want to determine position of the object on the projection plane, or in other words, if I want to translate any object in the space and whose coordinate position is, assume that p of x comma y comma z. If I want to translate this point P in a space onto the projection plane, then I need to determine what is the projection point on the projection plane, that is called xp, yp and zp. And here we have a projection reference point. So we are considering three things here. Assume that one point P is present in the space and its coordinates are x comma y comma z, and we have one projection reference point that is called camera position and its coordinates are x, y Z with respect to projection reference point. Now from this projection reference point, we are giving one point that is present in the space. Now we need to translate this point P position from the space to view plane. That is nothing but we want to project position of this point P on the projection plane with the help of projection lines. So wherever these projection lines are intersecting to the view plane with respect to this point P, then I can say that that is the projected point P on the projection plane P dash. So this derivation I did not derive in the previous video lecture. Today I would like to continue derivation of this particular topic, that is projection of a point P on view plane, that is called P dash. So directly I'll go to that particular topic here. So this slide I was not explained in the previous video lecture. Today I would like to continue this topic. Now we are discussing about determining perspective projection coordinates on the view plane. So when we are using perspective projections in our OpenGL program, we know that the property of the perspective projection is when two objects of equal size is placed in the space. When I translate the coordinate position of both the objects on the view plane, I will get one object of smaller size and one object of the larger size on the view plane. So this size of the projected two line segments, it depends on the distance between projection reference point to the view plane. If any object that is nearest to the view plane, as I said in the previous video lecture, it looks larger, and whichever the object is far away from the view plane, it looks very smaller. But the both the line segments assume that having same size, but the distance between projection plane and that line segment is different. So different distances will create different size of the object on the view plane. So now today we need to determine what is the coordinate position of those objects on the projection plane. So this is the derivation. So first I written Roman number 1. Whenever we want to determine what is the perspective projection coordinates on the view plane, first we need to determine what is the projection of the point on view plane. That is nothing but I am telling that only, right? If you want to determine position of the point P on the projection plane, here we need to consider three things. Consider a point P in a space, and this point P is, we need to assume it is a one object having its coordinate positions are x, y, z. This is the first parameter. Next we have a one projection reference point. This R is called projection reference point, or origin, or camera position, or eye position. Means we are looking this object P from the direction R to P. So capital R represent our origin or camera position. Means we located camera at that particular position, and we are viewing this object P from this direction, and whatever the dashed line I drawn, those dashed lines are called projectors or projection lines. So whenever this projection line intersect to the projection plane at the point P, then we will get P dash. Now our aim is we need to determine this P dash only. That P dash having its coordinates xp, yp and zvp, where zvp is some selected position of the view plane on z-axis. That is called zvp. And please you remember, whatever the dashed line I drawn, these dashed lines are perpendicular to the projection plane, or dashed line is perpendicular to the view plane. So when dashed line is perpendicular to the view plane, we are viewing the point P about the z-axis. I will repeat, we are viewing that point about the z-axis. Means that the third dimension is nothing but z-axis, right? So when we are viewing that object about the z-axis, then whenever that projection line intersects with the projection plane with respect to that point P, I can say that that is the projection of the point P or projection coordinates of the object P on the view plane. So this is our aim of this particular topic, or this is our aim with respect to this concept. So as I said in the previous slide, we have P dash and we have R and we have one point P in the space. And please you remember, this ZDP represent, we selected one intersection point on the z-axis to this projector or projection lines that will give what is the projection of point P and its position xyz to the projection point P dash, and its coordinates are xp, yp, zvp. So I drawn dot. This dot is there in the space. Same dot or same point I translated on the view plane, and its point is nothing but P dash, and its coordinates will become xp, yp and zvp. So these are the parameters we need to consider whenever we are determining perspective projection coordinates. So let's begin with the derivation. Now, whenever we want to determine what is the projection coordinates of any given object in the space, we are using parametric equation. So let us consider we are projecting a point P on the projection plane with the help of projection reference point R. Then I will get one straight line here. This straight line is nothing but our projection lines. Now we need to derive this particular concept only. Now we are using one parametric equation here with respect to projection line from R to P. So R, please you can see that R is our projection reference point, P is nothing but our object in the space. From the point R to P, we are using our parametric equation. So I will substitute. I will determine what is x dash and y dash and z dash by using parametric equation. So with respect to parametric equation, x dash is nothing but it is a difference between the x object coordinate, x axis object coordinate with respect to the difference of x axis coordinate of the given object with respect to x axis coordinate of the projection reference point, and it is multiplied with some constant called u. So this is x dash. Similarly, y dash is y minus y minus y projection reference point into u, and we'll get third equation z dash equal to z minus z minus projection reference point into u. So what is this z means? This is the z axis or z coordinate of the object, and projection reference point is, it is the z coordinate value of the our camera or our synthetic camera or our projection reference point or our origin of the camera. So when we are using some constant u, its value should ranges from 0 to 1. Means your u value in parametric equation, it should be greater than or equal to 0, and its value should be less than or equal to 1. Then we will get the two ends. As you can see that here I written clearly whatever x dash, y dash, z dash we are determining, this is nothing but coordinate position of any point along the projection line R2P. So we are determining here x dash and y dash and z dash. This is the projection coordinates of the point P on the projection plane. So as you can see that we have a three parameters. P is a object in the space. P dash is this object position is translated on the view plane. R is our projection reference point. And this whatever the line segment I drawn, this line segment is nothing but projection lines. But in real camera, it is called rays. Now I will substitute u value with two different values. If I substitute u value equal to 0, then we are at the one end of the line segment called P. When I substitute u value 1, then we are at the position of P, the line PR. Means here, means we are at the position from the line P dash R, not PR, P dash R. Means whenever you are substituting u equal to 0, you are at the position P. When you are substituting u value 1, you are at the position R. So P and R is nothing but two ends of the line segment. P represent first end point of the line segment of the projection line. R represent second end point of the line segment. Actually, it is not a line segment, it is a projection line. But for explanation purpose, I am telling it is a line segment. Means it looks like a straight line. So I am telling it is a line segment. So let us begin with determining projection coordinates of the point P called P dash, that is x dash, y dash, z dash. Then you substitute u value equal to 0 in these three equations. Equation 1, 2, 3. If you substitute u value equal to 0 in these three equations, then you will get new equation, that is x dash equal to x, y dash equal to y, z dash equal to z. This is z dash here, I written wrong. Z dash equal to z. So this is nothing but after substituting u equal to 0. Means when you substitute u equal to 0, you are at the position P. Means when you are at the position P, definitely whatever the x coordinate is there, that will become x coordinate of the P dash. Whatever the y coordinate is there with respect to P, that will become y coordinate of the P dash. When you substitute u equal to 1 in equation 1, 2, 3, see the equations. When you substitute u equal to 1 in equation number 1 and 2 and 3, you are at the position R. That is, x dash will become x projection reference point, y dash becomes y projection reference point, z dash will become z projection reference point. Means After substituting u value 1, your projection coordinates will become equivalent to your camera coordinates. This is about the u value. And here I written clearly what is x dash, y dash, z dash when you substitute u equal to 1. When you substitute u equal to 1, your x dash, y dash, z dash will become x projection reference point, comma, y projection reference point, comma, z projection reference point. Now, what is our aim here means, our main aim is we need to determine projection coordinates of the point P on the view plane. Now we also know that we are viewing that particular object about the z-axis. When you are viewing that particular object about the z-axis, then in a view plane, we need to select intersecting point of the point P will get our P dash value. And whatever the position we have been selected here, that intersection point P dash with respect to z-axis is nothing but ZVP. Means here ZVP represent we selected one position of the view plane, that is nothing but our P dash, and we are viewing in a positive z-axis direction, or we are viewing towards the negative z-axis. Positive z-axis is coming outside of the view plane. Negative z-axis is it's moving towards the view plane like this. Now I want to substitute z dash will become zvp. zvp. So when z dash will become zvp means we selected z-axis value on the view plane zvp and it will become equivalent to z dash. Then substitute z dash equal to zvp in equation number 3. So if you substitute z dash value is equal to zvp in equation number 3, here this is equation number 3 I substituted. Don't see this here, red color. See the blue color pen what I did the work here. Now after substituting z dash equal to zvp in equation number 3, then I will get what is the u value. So as I said in the previous slide, u is a some constant and its value ranges from 0 to 1. Now we calculated what is the u value when I substitute z dash equal to zvp. Then after calculating u, now we need to substitute the whatever the u value you calculated in equation number 1 and 2. Then you will get what is projection of the point P on the view plane with respect to x-axis and with respect to y-axis. So with respect to x-axis, I will get xp. With respect to y-axis, I will get yp. So I can say that xp, yp are the projection coordinates of the point P. This is called perspective transformation equations. I will give one name to this equation called equation number 4. Then we'll move to next second Roman number. So as I said the 3 Roman numbers, I hope you remember here when I was discussing this topic first time. So these are the 3 Roman number. First Roman number 1 tells that we need to determine projection of a line segment on the view plane. But now what we did, we determined what is the projection of a point P on the view plane. So what is the projection coordinate of the point P on a view plane means this is the equation we derived. This is the equation. See the slide. This is the Roman number 1. Means we calculated what is the projection coordinates of the point P on the view plane. This is Roman number 1. See the Roman number 2. Roman number 2 is here we need to determine position of the projection plane. So as we learned in the previous video lecture, position of the projection plane can be placed in three places. Three places as I discussed in the previous class. See the slide. This is the slide. For this slide, we need derivation. So the derivation is like this. Means we need equations. The equation is like this. This is the equation. I given Roman number 2. Roman number 2 says that we need to determine position of the projection reference point. So when you are calculating position of the projection reference point, this is third, I think. Here. Here. See the third point. I am not telling second one. Roman number 2 says third point with respect to this slide. I will repeat. Roman number 2 in the further slides is represent third point in this slide. Means we need to determine what is the position of the projection reference point. Then we discussed projection reference point here. These are the case 1, case 2, case 3. These are the projection reference point position we discussed as the theory. But now I am discussing derivation. So derivation is nothing but here. This is the derivation. Here. Please you see the derivation. Roman number 2 means what is the position of the projection reference point when you are capturing or when you are projecting a point P on the space into the projection plane. Then we need to, case 1, there are two cases are there. You can place the projection reference point with respect to two cases. If projection reference point is along the z-axis, when projection reference point is along the z-axis, substitute x projection reference point equal to y projection reference point equal to 0. Means when projection reference point is along the z-axis, we need to consider x and y coordinate value is equal to 0. Hence, substitute x projection reference point, y projection reference point is equal to 0 in equation number 4. So, see the equation number 4. This is equation number 4. If you substitute x projection reference point, this is the x projection reference point, y projection reference point is this. If you substitute 0, 0 multiplied by anything is 0 only. 0 is multiplied by anything is 0. Then you will get x p equal to this particular equation and yp equal to y into this particular equation. So as you can see this I written clearly, xp equal to this equation, yp equal to this is the particular equation. So now this xp yp represent position of the projection reference point along the z-axis. Case 2 says that if projection reference point is fixed at the origin, if you place the projection reference point at the origin of the world coordinates of the object, then x projection reference point, y projection reference point, z projection reference point will become 0. All three values will become 0. Then substitute x projection reference point, y projection reference point, z projection reference point in this equation, equation number 4. If you substitute this, then you will get the formula xp and yp. This case 2 indicates, please you see that, This case 2 indicates we kept projection reference point at the origin or at the origin. So if you place the projection reference point is at the origin, this is the equation you need to remember. Next we'll see case 3. Case 3 defines we need to determine position of the projection plane. So as we discussed, projection plane can be placed either with respect to ZVP value is greater than 0, ZVP value is equal to 0, ZVP value is negative value. These are the three places you can place the projection plane. But now where we are placing here means case 3 and 4, you see that. Case 3 and 4 with respect to Roman number 3. Case 3 says that if projection plane on xy plane, means what it means when you place projection plane parallel to the xy plane, z axis will become 0. So substitute ZVP value is 0 in equation number 4. So if you substitute ZVP value is equal to 0 in equation number 4, then our new equation will become XP and YP. These are the two equations you need to remember, and you can see this example. I think you remember this diagram. Now with respect to this diagram and with respect to case 3, we are placing projection plane at the origin of the world coordinate system. So here, see that here, here origin is there. We are placing with respect to x, this is x plane and this is y plane. We are placing projection plane parallel to the xy plane. When you place projection plane parallel to the xy plane, z value will become 0. So substitute ZVP value is equal to in 0 in equation number 4. Final equation you will get this. This is the final equation. Case 4 says that if all three coordinates are 0, all three coordinates are 0 means projection plane is placed at the origin. Projection plane is placed at the origin means x projection reference point is also 0, y is also 0, zdp also 0. Then this is the final equation. We get xp and yp like this. Now these are the three derivations we need to derive. So I would like to repeat. When we want to determine projection coordinates of the given object on the projection plane, we need to determine three things. First one is we need to determine what is the projection coordinates of a given object on the projection plane. Now what we derived here means with respect to this point of view, we calculated what is the projection coordinate of the point P on the projection plane. So if you understood how to project one pixel position that is present in a space having three dimensions projected on the projection plane into two dimensions, means converting three dimension pixel to two dimensional pixel on the two dimensional plane. If you understood this same concept, you can apply a image contains multiple or more than one pixels. So we did the derivation only for one point. So we learned how we can project a three-dimensional object having one pixel having three dimensions in a space. If it is projected on the projection plane having two dimensions, what is the projection coordinates we calculated? That is called P dash, and its coordinates are xp and yp. So this is the derivation today I discussed with respect to What is the projection coordinate of the point P or of the object on the projection plane? Next we determined or next we defined what is the position of the projection plane when we are using synthetic camera. So you can place the projection plane in three different places and you will get different equations. Today we discussed that we discussed only two equations. So you can place the projection plane about the z-axis value positive, zvp value positive, means that projection plane is closer to the synthetic camera when zvp value is greater than 0. When zvp value is equal to 0, it means that you kept that projection plane parallel to the world coordinate system of the object, and that projection plane is nearest to the origin. You can say that at that time z value will become 0. Third case, you can place the projection plane in the negative zvp value. When you place the projection plane in the negative z axis value, I can say that that projection plane is placed at the far clipping plane. If you place the projection plane at the positive z axis, it means that you kept projection plane near the near clipping plane. So these are the three positions are there you can place the projection plane. Or we also discussed in the theory, you can place the projection plane either between the projection reference point and object, or you can place the projection plane after object and after projection reference point. Third component, you can consider it as a projection plane. So we discussed this also. Third, we discussed or we determined what is the position of the our projection reference point. So we got two equations, case 1 and case 2. That case 1 and case 2 specifies where I can locate or what is the position of the camera we placed in the synthetic camera model. Means the origin of the camera is defined by the projection reference point. So today I would like to conclude projections topic. So just I would like to summarize what are the concepts we discussed till now with respect to with respect to projections. First, I explained why we need projections. I said whenever you want to translate or whenever you want to display a three-dimensional object on the screen of the monitor, we need projections. Then we classified projections into two types. One is parallel, one more is perspective. Again, parallel projections are classified into two types, like orthogonal and oblique. Again, orthogonal is subclassified into three types, like dimetric, trimetric, isometric, like this. This is the first classification we did with respect to parallel projections. Next, we classified perspective projections into three types. First one is called one point perspective, second is called two point perspective, third is called 3-point perspective. So these are the types of perspective projections we will get whenever our projection lines are parallel to either one principal axis or parallel to two principal axis or parallel to three coordinate axis. Next we discussed what is the shape of the viewing volume either in case of perspective projection or in case of parallel projection. So as I explained, shape of the weaving volume in case of parallel projections is like a parallel piped structure, and the shape of the weaving volume in case of perspective projection is like a frustum, or it's like a pyramid, or it is like a cone type structure. Instead of telling cone is not a right word. I can say that pyramid. It's like a pyramid type of structure. And weaving volume defines whichever the part of the object that lies inside the weaving volume within the range of near plane to far plane and four sides of the view plane. If the object is present within the four sides of the viewing volume and front near plane and far plane, then only that object is visible on the screen of the monitor. This is the shape and structure of the viewing volume in case of perspective projection as well as parallel projection. Next, we discussed what are the perspective projection coordinates. Today we discussed that only. And we also discussed what are the inbuilt functions we are using with respect to three-dimensional weaving. So with respect to three-dimensional weaving, we are using four different types of three-dimensional weaving functions to project three-dimensional object on a two-dimensional view plane. So in turn that object is translated from view plane to the screen of the monitor like this. So we discussed four types of functions like GL ortho that will take 6 parameters as input and it will create one parallel piped weaving volume and it generates parallel projections. Next, we discussed two types of perspective projections functions like GL frustum and like GLU perspective. These are the two inbuilt functions we are using in OpenGL program to project three-dimensional object on a two-dimensional view plane. And the last one, we are using one more OpenGL function called GL lookat. This GL lookat is a one more type of function we are using in case of OpenGL to project three-dimensional object on the two-dimensional view plane. So this is the completion of projections topic. So in my next video lecture, I would like to start visible surface detection algorithms. Thank you.